Yeah. So I'm handing over the presenter right.
Sure, sure. Okay, hello everyone. I hope all of you are doing good. So we will be starting in 1 minute, right? I'll just wait for people, some more people to join in, and then we'll start. And today, as I mentioned yesterday, we are going to cover regression, and regression will take whole session today, right? And next week we have three sessions, right? We have three sessions next week. Yes, so we will be
Minute,
covering,
right?
I'll just wait
Decision tree.
for then some more algorithms like KNN, K nearest, and then clustering, and of course factor analysis, which is left yesterday, which we could not do yesterday. Okay, so I'll just wait for 1 more minute, and then we'll start. Okay, so all of you can see my screen. All of you can see my screen. Yes. Okay, so let's start with correlation. I remember we had not discussed correlation earlier when we were doing the basics of statistics, right? So, what is correlation? Can anyone tell me what is correlation? It's there on the screen though, but yes, if you have any idea, let me know, else I am going to discuss it anyways, right? Okay, it measures the degree to which relation between one factor and another. Okay, Vaibhav, I would rather just replace it with one variable and another, right? Not factor. Okay, Sachin, after today's session, but I will, because today's session we do not have any break. I mean, break in the sense we'll take a 15-minute break, but it's running. I'm not shifting from one. I'm not doing two models like yesterday. We did two models, right? PCA. So it's one model and it's going to be a continuous session. So I'll take break towards the end, right? Okay, let's start. So correlation is a term that describes the degree to which two variables move in coordination with one another. If the one variable moves in the same direction, if if the two variables they are moving in the same direction, right, we call it positive correlation. For example, you can see uh, in the charts below, right, these are positive correlation because here my x and y variable both are increasing, but the degree is varying. You will notice the degree of the is varying. This is here the strength is more here because both x and y are increasing with the same intensity. Here, as x increases, there is an increase in y, but yeah, the strength is a little bit less. And here you can see the strength is more than this one, but less than the perfect correlation. This is called perfect correlation. Okay, so it measures. Yeah. Mm, they, so this is positive correlation, but when both the variables move in opposite direction, means as one variable increases, the other decreases, we call it negative correlation. And if there seems to be no relation between them, right, we call it no correlation. Means as one increases, the other might increase or might decrease, we don't know, and there is no relationship as plot you can plot, right? It does not give you an idea whether it's a positive correlation or a negative correlation. So then you call it no correlation. The correlation coefficient is represented by a small r. Now this is again a standard notation, small r, and it ranges between -1 and 1. So whenever we have a correlation which is negative between two variables, we'll have correlation values less than 0, but between 0 and -1. When there is no correlation, r is equal to 0, and when it is positive, r is equal to 1, right? Or between 1 and 0. And r is equal to -1 means perfectly negative, r is equal to 1 means perfectly positive correlation. Okay, clear? Correlation is clear to all of you? Now, why did I choose to do correlation here? Because when we do regression, we are going to check the correlation between multiple independent variables to find out the redundancy, to find out whether and we'll see how correlated variables can make your regression model weaker, right? We'll see that today, how multiple variables which are multiple independent variables that are correlated, right? They increase the variability of the coefficient of the um regression coefficient in the regression equation, right? And when the variability of the coefficients in the regression model increases, it reduces the strength of the model, right? So correlation is useful because it helps you find the relationship between variables, right? Relationship variables have, you can make predictions about the future. A correlation between variables indicate that as one variable changes in value, the other variable tends to change in a specific direction. Correlation coefficient measures both the direction and the strength. We have seen direction is measured by plus and minus, and strength is how closer the correlation coefficient is to 1, 0, or -1. Right? Now, this is important. Correlation is usually used to identify two independent variables and identify the variable that can be eliminated, right? So with correlation, we try to find out the two independent variables which are correlated, right? And which one of them I should be keeping in the final model, and which one of them I can remove from the final model, right? That is why correlation is used for. Okay, some example of correlation: height and weight of people, number of deaths in a city and road accident, time spent studying and scoring percentage, right? So these are some examples of correlation. Clear? Correlation is clear to all of you? Any question related correlation? Anyways, we are going to do it in detail. If you don't mind, can you explain correlation just now? Bharat, correlation is simply measuring how the relationship between two variables. The relationship between two variables means as one increases, the other increases, or as one increases, the other decreases. If both of them are increasing, we call it positive correlation. If one is increasing, the other one is decreasing, we call it negative correlation. And if there is no such relationship found, we call it no correlation. Okay. So clear, Bharat? Right. So I just reviewed it a little bit fast because we have to cover a very long topic, and I cannot, if we are not able to cover regression, or we will have, I cannot extend this to the next class, because otherwise the entire momentum and the entire that uh, thing is lost. I will only have to extend the session. Okay, so please understand, we have to cover this, right? So I'm not saying that you are not allowed to ask the doubts, right? At all, I'm not saying that. But please, when you are asking something, you think that it is important right now. Like Sachin just mentioned, doubts, I will take doubts, but later, right? So not in between. Okay. So thanks for the cooperation, and over to regression, right? So yes, regression. So as I said, we'll be doing linear regression, right? So what do you mean by regression? I'm sure some of you would have uh, done this topic in your high school or maybe later, right? What do you mean by regression? Yes? Anyone? Prediction, okay. Regression is linked with prediction, right? You can predict the, in fact you predict the variables, right? Observed and expected pattern, mm, mean relation. Sorry. Okay. May, did you said may? Yeah, this will have been predicting the relationship between variables. Correct, right? So let's, yeah, I think those who have mentioned, it's right, right? Whatever you have mentioned is right, but we are going to do regression in great detail today, right? We will understand what are the way, how do you measure the strength of the regression, right? We will also discuss the topic of multicollinearity. We'll also discuss the topic of overfitting, right? Right? But yes, whatever you're saying, as a layman or as from today, you will not be a layman because we are going to touch each and every aspect of regression. Okay, so you'll have a very deeper understanding on what regression is. Okay, so let's start regression analysis, right? Statistical technique used to predict values, as some of you also use this word prediction, right? Yes, it is a technique to predict values, but the important thing here is it is predicting the the dependent variable which is continuous in which is continuous, right? So my dependent variable is not categorical, it is a continuous variable. For example, price, sales, right? Age. Is that clear? So that is an important point here. If the dependent variable, if my dependent variable is not continuous or it's categorical, then there are other techniques like logistic regression can be used where the predictor variable, where the dependent variable is not continuous. Is that clear? That's the very important point for regression. Okay. Okay, fine. So a regression is a predictive modeling technique used to investigate the magnitude and direction, okay, magnitude and direction of a possible causal relationship between observed pattern, means the dependent variables, and the independent variables, okay, likely to have an impact on the observed pattern. So we observe the values of uh, y variable, and then based on some independent variables we try to predict how these independent variables can impact or can have an impact on the dependent variable, and how can I model that impact so that in future when new data comes in, when new x comes in, I am able to predict the value of the dependent variable. Clear? So, but and it also models, as it said, magnitude and direction both. Just like correlation we just discussed, magnitude and the direction both, right? So, regression model can help you investigate that. The dependent variable, usually y, is also called response variable, and independent variable, usually x, can be multiple also, are called predictor variables. Okay. Now, regression indicates that significant relationship and the strength of the impact between the dependent and independent variable. Notice the word significant relationship. Significant, whether a variable is having a statistically significant relation, coming back to inferential statistics, right? So you will see in the regression output, we will have p-values, and of course, if the p-value, just like that happens in hypothesis, if the p-value is very small, it means that there is a very strong relationship between the dependent variable and the independent variable, right? And if the p-value is large, right, it means the variable is insignificant. The more the p-value, it means the more the variable, independent variable, is insignificant in determining the value of y. Okay, that is why we have done, because of these important things, because we have to figure out which of the variables we should be putting in the regression model and which of the variables I should be moving out. And only this hypothesis testing will help us determine whether there is a significant relationship or statistically significant relationship between dependent and independent variable or not. Okay, so regression is used in forecasting, time series modeling, finding causal relationship between variables, right? And as you can see in this picture, this person is trying to fit the regression line between the scatter, and it's not that easy task. Okay, it he's kind of struggling because the data keeps changing, so every time he has to um alter the model. Okay, so okay, now what we are going to do is we are going to learn regression with the help of this case, and it's a very famous case, uh, wherein case of predicting the price of a French wine. Okay, we're going to see. I'll just give you a background of about this case, and then we'll proceed. On March 1990, Orley Ashenfelter, a Princeton economist, Princeton economic professor, claims that he can predict wine quality without tasting the wine. So all of you know, or I mean, people those who are interested in wines, they must be knowing that there is a big industry called wine tasting, right? Wine tasting is also industry, right? People those who are they are wine tasters. They tell, after tasting the wine, they tell how this wine is going to be in future, whether this wine is going to be of high quality or a low quality, right? Depending on, and as we store in more wines, because more is the age of the wine, better is the uh, better it is expected to be sold at a higher price. I mean, those who know, I'm just giving you a brief. Those who don't know, right? Yeah, they get paid too, of course. They taste wine and they get paid too for it, for their accurate predictions, right? So this person, Ashenfelter, challenged the best of the wine tasters of that time and felt that his predictions are more accurate than the wine tasters who felt threatened by his claim, right? A very interesting case. That's why I've taken. Otherwise, I also have uh, one more example which we will not be covering, and I have given to you. You can uh, I would expect, like, it's a weekend, so I would expect you to go through that second case also, Boston, right? In this, we are trying to predict the price of the Boston houses, something like that, right? But we'll cover this today. Regression, wine tasting. Okay. So now, what happened? Yeah, Bordeaux. Bordeaux is a region in France popular for wine producing, right? While this, I'll quickly run through this. You just hear, because it's a background about the case. While this wine has been produced in much the same way for hundreds of years, there are differences in the price and quality from year to year. That year to year that are sometimes very significant. Bordeaux wines are believed to taste better when they are older, so there's an incentive to store young wines until they are mature. The main problem is that it is hard. Now, see the problem here, right? The main problem is that it is hard to determine the quality of the wine when it is young just by tasting it, right? Hence, the taste since the taste will change so significantly by the time it is mature that it will actually be by the time when it is consumed. This is why wine tasters and experts are helpful, right? That is why wine tasters, they taste the wine and then predict which one will be uh, which one will be the best wine later, or which one could be sold at a higher price later, right? Now, can analytics model this process better and make stronger predictions? We'll see in this case. Okay, you got the background, all of you. What is the background, right? So Ashenfelter was the one who challenged them and said, I can predict the price of the wine, I can predict the quality of the wine without tasting. And what he did was, Ashenfelter used this method called linear regression. Why linear regression? Why linear regression? Because my dependent variable is price, which is a continuous variable, right? No, this is a very important point. I'm again repeating, we can use regression only when the dependent variable is a continuous variable. If my dependent variable, let's say I'll give you an example here quickly. If my dependent variable is not a continuous variable, for example, predict I want to predict whether the customer coming to a bank is a good customer or a bad customer. I want to model this. So is my dependent variable continuous in this case? Good and bad? No, it's a categorical variable. In such cases, we cannot use linear regression. There are other models we are going to discuss, like decision trees, random forest, and logistic. Okay, clear, right? So Ashenfelter used the model called linear regression and predicted a, a method called linear regression and predicts an outcome variable, also called the dependent variable, based on a set of independent variables. So what he did, he tries to predict the outcome variable. Now our outcome variable or dependent variable, which which actually simulates or which actually approximates the quality, is the price. Of course, higher the price means better the quality, right? So typically price approximates the quality of the Bordeaux wine. Now, some independent variables that he used: age, age of the wine, then weather conditions in which that barley was grown. He used those, the data around the weather condition, like average growing season temperature, winter rain, and harvest rain. Along with the age, he used these three more variables to to create a model with which he will be able to predict the price of the wine. Is that clear? Right? Okay. Now, this is the data what he analyzed. What he did was, along for price, he he put all the independent variables with price individually. Right? He has put all the independent variables with price individually. Age of wine, average growing season temperature, winter rain, and harvest rain. Right? When the barley was harvested, when there was winter, when they were grown in winter, what was the rain, right? And so this is the data that he observed, right? Okay. So now what we are going to do is, we are going to take one variable, average growing season temperature. Okay. What was the average growing season temperature that was taken, that was measured, right, with the price, and we are going to start understanding regression from there, and then we will bring in more variables after we understand the concept with one variable. Okay, because it's easier to visualize, it's easier to understand the relation between dependent and independent when there is only one variable, right? uh, as we put in more variables, then you just extrapolate that concept. Okay. Okay. So okay. Yeah. So let's say I I give you this chart, right? Right. Let's say I give you this chart. Let's talk about this only, right? I give you this chart and I ask you what we are trying to do with regression. We are trying to predict the value of a dependent variable, which is price. Now just concentrate on this chart. If I give you this chart and I ask you what can be the best price estimate that you can make, or you have to predict the price, right? No other information I give you. I just give you this chart and I ask you predict. You have to predict the price of the wine. What can be the best estimate you can make? No other information I give you. I'm saying what is best you can do. I'm not saying that you have to predict it accurately. I'm saying what is the best that you can do. You have some price data, you have some price numbers, right? For different average growing season temperature, you have some price values. So what can be the best you can do if you have only this data? We can check, just think, we can check temperature and check, sorry, check temperature. No, I'm saying we are just and evaluate price. Okay. Any other guesses? Draw a line covering maximum points and predict. Draw a line covering maximum points. But if you try to cover maximum, that is what we're trying to do. We are trying to predict. I'm saying no other information is given. Give me a price estimate. We can check the constant growing temperature. Okay. Okay. Let me tell you, and all of you would agree with that. If I have this data, I do not have any other data, and I ask you, I have another data point, right? Less variance of temperature, okay, right? If I have another data point, give me the best price estimate. Will it not be the average price of all these points, price points? The best. I don't have any other information. What can be, what you can do best? See, now that's why I just thought that maybe you try and think, but yeah, that's okay. And right now, see, this blue line is my best regression line, which we are going to come to, right? But if I don't have any information, what can be the best price that you can uh, estimate? Isn't it the average of all these price points, right? Yes, all of you agree? Exactly. Yes, Angela said. I think Angela mentioned it correctly. Yeah, right. Okay, Angela also just. I think she wrote after I spoke. If you have given that answer before I spoke, then definitely a very good uh, response. That is what I was expecting. Okay. So everyone agrees. I do not have any information about density, about other variables, about the best estimate I can do is take an average of the price, right? So this is from where we start our regression, and this is our baseline regression model. We take this as baseline regression model, right? No information is given, so this red line is my base model. Okay, so any other data point comes in, best estimate I can make is average. Take an average, right? And if you remember the calculation also for regression, I don't know, some of you would have done that in your high school. You subtract, you first calculate the mean of y, x bar and y bar. We calculate the y bar, right? This is y bar, okay? Mean of y, okay? Baseline model is a model that you can best guess when nothing is known, predicts the same price irrespective of the x, and does not use any other variable. So whatever is the new x coming in, that is average growing season temperature, my price remains constant because it's an average, right? Now, when you have this, we'll see how what changes we make so that we are able to improve this model and make it from red line to blue line, okay, which is the best regression model. That is what our purpose is. That is what we do at the back end, right? Because R will not do this on the front. R will just give you the answer. But what is happening at the back end, we are discussing that. Okay. Now, so one variable regression line, regression model is, because regression is a linear, we are doing linear regression, so it's going to be an equation of a line y is equal to mx plus c. I'm sure all of you know it, right? Y is equal to mx plus c. B0 is here the constant, right? B1 is the coefficient of x and e. Then there is this e term, error. What is this error term? We are going to understand this first and then we will move further, right? So whenever we write a regression equation, we add this term e. E is the error of the ith term, right? So, and the best model is the one that has the smallest error. We'll see first, but let's understand the different types of errors we have. Okay. Okay. So what are the different types of errors that you can have? Let's say I have this x variable and y variable, right? This is my x variable, this is my y variable. Now, measures of regression model used to check, yeah. So errors, as I said here, see, the lowest or the smallest is the error. The better will be the model, right? This error means what is the difference between the predicted y predicted and the actual y, right? So lowest is going to be the error, the better will be the model. So that is why we are understanding what are the different types of errors, so that we can, based on these errors, we can check how robust our regression model is. Okay. So first type of error. Okay. First, what we'll do is estimated basis regression. Okay. Wait. Okay. Yeah. So this is my x, this is my y, and this is my y estimate. I mean, this is completely you can say cooked data, and just an example, just to show you the different types of error. Okay. This is the value of actual y, and this is the value of predicted y. Okay. That came from the regression line, estimated y. Okay. Now let's see how do we calculate the different types of errors. First, some of the errors from the mean, right? Some of the errors from the mean. So how do you calculate that? I calculate the error from the mean of each value of y. I calculate the error from the mean. Means I calculate the mean of y, which comes to be 4, right? This, if I calculate the average, it is coming to be 4. Now from 4, I calculate the error of each y. It comes to be 2 here, 0, 1, 0 and 5. Clear? This is a very simplistic way of calculating error, right? Then absolute error. What is this absolute error? Absolute error is simply the difference between the predicted y and the actual y, right? It is the difference between predicted y, which is 2.8 here, and the actual y, that is called absolute error. Okay. And notice again, it is in absolute, right? It is only measuring the extent of the error, not the direction of the error. Okay. That difference is on, it could be on one side or the other side. It is not measuring that. It is just giving you a absolute value of the error. Clear? Okay. And once I take a total, I get that number, total absolute error. Direction of the, okay, Vaibhav, direction of the error means, notice here, I am saying this one, right? Here I am at measuring the error from the mean, right? So if 4 is my mean, my x value, my y value is 2. It is on left side, y is on left side, and if 4 is my mean, 5 is my actual value. So actual value is on right side, right? So can you see here the direction is also there. One is having a minus side, the other one is having a plus sign. So it is on two different sides of that mean. Okay. So but this absolute error, notice I have put ABS. It is not measuring the direction minus or plus. It is just taking an absolute of the errors and totaling it. Clear? Okay. Now mean absolute error. Very simple. I take this total error 3.2 and divide by 5. That will become my mean absolute error, right? 3.2 divided by 5. It comes to be 0.64. Or you can individually add them and again taking an average of all of them. It's the same thing, right? Or either I just take 3.2 divided by 5. It's also going to give me that same number. This is mean absolute error. Okay. Then comes a very important measure. See, these are very crude measures, absolute error, right? But when we have to do regression, we have to come to a very refined measure or a very, you can say, a measure that error that actually gives you uh, that you can analyze even in complicated models, right? These are very simplistic measures, right? So then comes sum of squared errors, right? What we do is, as if you remember in the first session, I told you how to read these. I think we did this in central limit theorem. Remember? All these statistical terms you read from the back, right? From the right side. So errors, squaring it, and then doing the sum of it. Okay. So first I calculate the errors and square them up. So this was my error, 0.8. This difference between these two, 0.8, and I do a square of it. So it comes to be 0.64. Similarly, I do it for all others and then I sum them up. So that becomes my sum of squared errors, right? Now, why am I squaring it? Because again, to do away with the direction, okay? Because otherwise what happens is some of the some errors are going to be on right side positive, some will be on negative side, and if I don't do a square of it, both of them are going to settle them off, right? Minus and plus, they are going to settle them, set off, and I will, yes, I will not be able to analyze the um deviations, right? I will not be able to analyze the errors. Okay, that is why first I do a square and then I sum it up. Okay, next, now here there is a issue with this sum of square errors. Small issue is there that I have done a square of it, right? So when I have done a square of it, I am not at the level of y, right? Can I measure the squares? Are the squares comparable to the actual numbers? You go to another level, you are squaring it, right? They are not comparable, right? Everyone agrees? They are not comparable, right? So to make them comparable, right, so that I can actually compare, I can have some comparable numbers, I do a root of it. If I squared it up and I do a root of it, square root, right, I will we now at the same level as y. So now at least I can make some sense of, okay, this is my average error 0.69 when these are my numbers. At least they're comparable, right? 2.4 and these are not comparable because this is a squared number, right? Is that clear? Why do we use root mean squared errors, right? So, so I do under root. I just to this SSE, I just add a under root, right? Or square root, and we get a root mean square error, right? So if I do a SQRT, wait, not this. Root first we calculate the sum of squares, and then we do a root of. We take a average, and then we do a root. Okay, clear? So then mean absolute percentage error. Now this will give you what is the mean absolute percentage error. Now we have the root absolute error, we have the absolute errors, right? What is the percentage error for each term? It's simply, you can see this, you can see this, I mean, you can calculate it manually also in your mind. It is a 40% error, right? Because 0.8 upon 2, this is a 15% error. 0.6 upon 4, this is 20% error, right? So that is mean absolute percentage error. Clear the different types of error we can have, but we are going to concentrate more on these two, this one, and then I'll also introduce another coefficient of correlation, which also helps us in understanding the strength of the regression model, right? Coefficient of regression, right? Okay. So these are just the definitions I've given. As I mentioned, RMSE, MAP are most used in the industry. In fact, SSE is also used. So these three are the most used. Okay, depending on it depends from industry to industry and from case to case. Clear the different types of errors? Any questions around errors? Let me know as we'll proceed. Okay. Okay, great. Right. So let's see this. Though I've already explained, but we are going to just dig deep and understand these errors now. Right. Sum of squared errors. Right. So now coming back to our same example, if I calculate the error for this average line, SSE, sum of squared of errors, means it measures the quality of the regression line. Line having the minimum SSE is the best fit line for a set of observations, right? So minimum, the minimizing means minimum the error, minimum the SSE, better will be the line. So for this red line, which is my baseline, SSE is 10.15. Sum of squared error was 10.15. Okay. When I started putting in more variables, I started improving on this line, blue line. I came to a blue line, and there my error was 6.03. Sum of squared error was 6.03. Then when I was able to convert this into a best fit line, green line, this was my sum of squared errors. So you can clearly see as we move from baseline to the best fit line, my error, sum of square errors is minimized. Now, even if I go now again, if I, uh, right now I was moving this way, right? Now, if I go on the other side of this line, my errors are going to start increasing. Okay, this is the least value of SSE that I can get, and that is why, and this is the error that will be given by my regression equation. Okay, right? So SSE. Okay, next. Now pictorially, I've just shown you what is SSE. Simply sum of squared of errors. So if this is my regression line, black one, and this is the error. This is the error, right? This was my y actual. and my line predicted this value. So this is my error. You just square it up. So pictorially, this is just shown pictorially. Otherwise, you'll have numbers, right? So pictorially, if more squares, bigger squares you see, it means more error is coming. The smaller squares you see, it means less error is there. Okay? So this is just showing it pictorially, the errors pictorially. Okay. Now coming to, as I mentioned, root mean squared error is a better measure. But yeah, we use SSE, we use RMSE, all these we use in different industries depending on the practice they are doing and depending on their own other, uh, you can say, reasons also, right? What is best depending on the, it could depend also on the type of product, right? Various other reasons, right? So SSE can be hard to interpret. Why? Because as I said, once it does not have, units are hard to understand because it is squaring it. Second, it depends on n. N means if I have more observations, because it's a positive value, it is only going to increase, right? So more the n, larger will be the SSE, because it is only going to keep on adding. There are no negatives in this, squaring it up. So more the n, larger will be the SSE. That is why SSE is hard to interpret. But if I take a root of it, I get RMSE. At least I'm able to do away with that squaring impact, and I bring it to the same level of the y by doing a under root. So what I'm doing here is I'm just normalizing, oh sorry, normalizing it, and also here square root and root mean is dividing by n also. I'm dividing it by n also. So one, I am normalizing the impact of n, and second, I am also normalizing the impact of square that I have done, right? Clear? Root mean square error, root mean squared error. I have normalized it and brought it to the level of y. Root mean square error is clear. That is why it is considered as a better measure, because we have normalized it. Okay. Now let's take a deeper look. Let's go one level deep and understand how these errors are, and what better measure can we come up if we analyze them, these errors. Okay. We are going to understand the errors with the help of this y value. Okay, actual y, right? So what I'll do is I'll just take up this. This is my actual y, this one, right? And this was the value of y predicted by the base model, right? So clearly this becomes the one in red bracket, right? This becomes my total error. Yes, we call it total variation, right? So if I deduct each value from the mean value, it becomes my total variation, right? It is called sum of squared of the total, right? I do a square of it, it gives me the total variation, right? Now comes in my regression line, green one, and it is able to predict the value of y, this one, this green dot, right? So has it done some improvement over the base model? Yes, it has added value. It has done some improvement over the base model. Can I have response? Do you think there is an improvement on the base model? So this regression line has been able to add some value. This part that it is explaining, or we call it explained variation, means the part that the regression line is able to explain and add value over the mean, over the base model. That is why this was considered the base model, right? You can easily see this green part is the explained variation that my regression line was able to capture. The variation my regression line was able to capture is called explained variation. Clear? And I am left with something that is called unexplained variation. Is this clear? Explained and unexplained? Now think in terms of, I'll not go to the next slide. Rather, I would want you to think. If I have some explained variation and unexplained variation, right? What do you think my best fit line should do? Best fit line. What do you think it should do? In terms of explained and unexplained, it should minimize the unexplained variation, right? Right? Of course, see, I first of all understand this. I cannot pass a single straight line, linear line from this scatter. So, of course, gone is that case if you think that I'll pass a line from all of them and there will be no variation. We are right now doing linear model. Okay. So, I can pass a best fit line, and the best fit line will be the one which will have, which will show the minimum unexplained variation or maximum explained variation for all the points, all the data points. Yes, everyone agrees with this. Yes, right? And that is what a best fit regression line does. So how can I get to that? How can I check whether this how can I check the best fit regression line? If I have these, I am going to add all the explained variation divided by the total variation, right? If that is maximum for different lines, or if that is maximized, it means my task is done, right? That is my best regression line. Clear? Right? And that is what is calculated by coefficient of determination, R square. Right? I think I earlier said coefficient of correlation, something like that, right? My bad. It's coefficient of determination. Now understand, this is a capital R. Small r in statistics means correlation coefficient. This R square measures the strength of the regression line. How strong is the regression line, and how is it calculated? SSE. What is SSE? Unexplained, right? Upon total SST and doing a 1 minus of it. So it is equal to SS ESS, right? It is equal to ESS upon total, right? 1 minus, right? So I am minimizing the errors here and subtracting it from 1. That will give me R square. Is that clear? R square is a notation, right? We are not squaring anything right now here, but yeah, we are subtracting because we are dealing with squares, so we call it R square. Okay? Clear how R square is calculated? Right? So R square is interpreted as the proportion of variance in the dependent variable that is predictable from the independent variable. It ranges between 0 and 1. Means how much of the variation, how much of the variation my regression line is able to capture. That gives me my, that gives me the R square. So maximum it can go to 100% and minimum it will be 0. So R square lies between 0 and 1. Clear? And it clearly, I've shown you also, it clearly captures the value added, right? The value that my regression line is able to add over the base model. It captures that, right? Unitless and universally acceptable. Why R square is the, better than earlier? Because though it is coming out of, I'm using SST and SSE, right? But it is unitless, it is in you can say in percentage terms, or you can say it's in decimals, right? And so it's unitless and hence universally acceptable. R square, if R square is 0, it means there is no improvement over baseline. If R square is 1, I'm able to predict perfectly, though we are not God, so we cannot bring R square to 1. We can bring it closer and closer, but we cannot bring R square to 1. Also, we will understand why we should not be chasing R square, right? We by only I R square, I should not be only looking at R square. We'll understand that also. Okay? Okay. So till here it's clear. R square is clear. What is R square? How is it calculated? What does it explain? I mean, what does it signify? Okay. R square measures the strength of the model, right? Greater the value of R square, stronger the regression model explains or fits the data, right? So this is, I've already explained it. R square is handy, seemingly intuitive measure of how well your linear model fits a set of observation. However, R square does not tell us the whole story. We'll see how. We cannot completely rely on R square, though of course it's a very good measure. Now see, that is why we say statistics is definitely, or data science is science, but yeah, it deals with social, I mean it's a social science, right? It also, we are dealing with business, which is not science, right? So we it is not as precise as any scientific notation, right? So even if we have R square, it does not tell us the complete story. You should evaluate R square in conjunction with residual plots, other model statistics, and subject knowledge. Very important. Subject knowledge. We'll also cover this subject knowledge part, subject area knowledge, in order to round out the picture, right? We'll understand why, along with data science, we have industry experts, right? We have industry experts in uh, working, when you are, when as a data science scientist you develop models, right? You are working along with industry experts. We are going to see that also in this case, wine testing case, right? Okay. So okay, R square does provide the strength of relation of variables, but does not provide a formal hypothesis testing of the relation. Means it does tell you, okay, this is my regression model, right? This is my regression line, and it is better, it is explaining this part, explaining, let's say, 80% of the variation, right? But it does not tell you which of the variable is significant and which is not, right? That is why we have to club R square information with other information also, right? So as we bring in significant variables, see, not all the variables that I am uh, that are my independent variables, not all of them will be significant in developing or in constructing a final regression model, right? Some of them will be insignificant, right? So when I take in only the significant variables, now we are going to check the significance using the p-value, right? So, but when I take only the significant variables and I calculate R square using only the significant variables, right? We call it adjusted R square. So adjusted R square is a better metric than R square, because it includes only the variables that are selected or significant in the model, while R square includes all the variables, whether they are significant or not, right? So we have improved R square a bit. We include only the variables that are significant. Clear? Difference between R square and adjusted R square is clear, right? Okay, great. Next, so this is just to show you that I think I've shown this earlier also. Yeah, so I don't need this. We can just do away with this slide. It's just comparing the. Okay, this is I've mentioned SSE, though it should be R square, right? Compares the best model with the baseline model. So I should have shown R square of the base model, R square of the best fit model. Okay, but anyways, we'll have it in the next slides. Okay, so is the concept clear? What is a regression line? What is it trying to do? How is it trying to capture the variance? How do we determine the strength of the regression line using R square? Yes, clear to all of you? Any doubt till here, let me know. Else we will proceed to the next part now. Okay, now till here, to explain the concept, I have used only one independent variable, right? Because our mind can easily visualize it, our mind can easily correlate it, right? Now, if I bring in, now let me bring in other variables, right? So, average growing season temperature, harvest rain, winter rain, age of wine, and population of the wine, population of France, right? These are the other variables that Ashenfelter used to create the regression line, right? If I bring them, it will be difficult for me to visualize, though the concept remains same, but visualization will become difficult. So we explain the concept with the single independent variable. Okay. Now when I bring in more variables, see what happens. My R square was when I calculated R square using a single variable, my R square was 0.44. When I calculate the R square with only harvest rain, it was 0.32 and so on. So these are R squares when I'm just trying to predict my price with only a single variable, right? Each of them using trying to predict price separately. Okay. So model based on multiple independent variables score over a single variable means now this is how my R square is if I am trying to predict the value of price using only one variable. But if I try to combine them, if I try to go to higher level, higher order regressions, or you can say multiple regression line, multiple linear regression, right? This is one variable. Till now we were doing one variable. So multiple linear regression, the equation becomes this, though this is only a theoretical part. But of course, can you make sense of this equation? It is just, I have just extrapolated with more x's, right? Okay. Now, when I had only AGST, average growing season temperature, my R square was this. When I used AGST and harvest rain, my R square improved. Again, I used age, R square further increased. But notice, as I kept on adding more variables, my R square is increasing, but at a diminishing rate. Can you see? Here the increment was very high, then further it became low, it became further low, and in the end, there was no improvement in R square, right? So adding more variables improves our regression model, and but diminishing return operates as the model as more and more variables are added. So do you think, looking at this slide only, do you think it makes sense for me to add all the 5 variables, or should I say add population to the independent variables? No, because I am not able to improve my model here, right? I'm not able to improve my predictive power of the regression, right? Explain variation, I'm not able to improve. Maximum it goes to 83. Okay, so it does not make sense there, right? Okay, going to next. Now, as I said, not all variables can be used, right? Some of them will see do not go well in the model, and you will also see that even the p value is indicating that there is no correlation. They do not have any significant relationship with the dependent variable. Okay, so not all variables should be used. Each new variable requires, why we should not use all variables as we saw it. First, each new variable requires more data. Second, now this is a very important point which we are going to learn. If I if I use all variables, right, and my only aim in the mind is to increase the R square. I just want to, I'm concentrating only on R square. That is why I'm just putting more and more variables so that I can maximize the R square, right? I would say even this can also be a good model. Why? It is very near to, if suppose bringing in winter rain can really, for two things. If capturing the data of winter rain is difficult, right? It's very resource of, I mean, it's very expensive in terms of resources. And second, if this bringing in winter rain complicates my model, right? Under that circumstances, even this will be a good model, right? These three variables, you have simplified the model and you are capturing a good amount of variation. Okay, but when we start chasing blindly, when we just start chasing R square, right? Okay, I bring in more variable because my R square is increasing. So I I am blindly just looking at R square, right? What we are doing here is, just a second, Nisha. So here industry knowledge, exactly, Nisha. That is what I'm saying. And in this, that is why I take this example, because it also has a tinge of that industry knowledge, right? Why industry specialists are there, we'll see, right? Okay, so let's continue. So if I just keep on chasing R square, right? What I'm trying to do is I'm just trying to overfit my training data, right? The data on which I'm trying to create the model, I'm overfitting it, right? We'll see what overfitting is, right? Causes overfit, higher I square on data used to create model, but bad performance on unseen data. We'll understand overfitting in the coming slides. So let's skip this point right now. We'll see later how to appropriately choose variables to remove. Fine, right? So overfitting. Now let's see what is overfitting. The case of overfitting. See, what happens is, what is overfitting? When statistical model begins to describe the random errors in the data rather than the relationship between the variables. Means I am just, my blind focus is only on reducing the errors or increasing the R square, right? I have just blindly started chasing R square. Notice here that I am developing a model on some training data, right? And if I just suppose, hypothetically, just think, if I just am able to, I'm chasing R square in my mind, and I am bringing in more variables, doing some variation, and I come up with a model that is like this. It is with a R square of 99.99. Very good model I have created, right? I have created a very good model, right? So what will happen when a new data comes in? Will this model be able to accommodate that new? Will that generalizability of the model be still there? No, this model I have trained, I have created this model based on training data, and I have tried to overfit it. Notice overfitting. That is why we call it overfitting. I have tried to overfit that data, which is training data. Now, when some new data comes in, my model is going to fail. Are you getting it? Why overfitting is dangerous and why we should not be just chasing R square, right? So it is we overfit, we over we create overfitted models when a statistical model begins to describe the random errors. We are just concentrating on errors. We will reduce the errors, right, to maximum 0.99. We will become closer to God, right? And in that entire process, I lose the generalizability of the data. Taking more R square data, sir, or different? Overfitting means taking more R square, means chasing R square. I am just concentrating on R square value only. I am saying I just try to focus that I just try and bring in more variables so that my R square becomes maximum. Okay, that is called overfitting. Bharat, understand this. If I have this model, if suppose this line, you come up with this regression line, right? And a new data now, and you deploy this model, right, to predict the price of the wine. Next year, new data comes in. Do you think this model will be able to fit or will be able to explain that new data? It is no. Why? Because it is only tailor made. I mean, it is created only to suit the quirks of the training data, right? I did not think about the generalizability that my model will. That is why remember that E component, why it is always written with a regression line, because you cannot have a regression line which is perfectly passing from the from the data. There is going to be a element of error. There is going to be, our regression line is best when it is generalized generalized, right? Overfitting a regression line, overfitting a regression model reduces the generalizability sorry, generalizability outside the original data set. Are you getting it? What is overfitting? Yes, Nisha, right? Is this point clear? Overfitting, what is overfitting? Everyone type O in the chat window if it is clear. Okay, great. Thanks for the response. So, overfitting refers to a model, overfitting to a model that models the training data too well. I am I am just trying to fit into the training data too well, right? I am losing on the generalizability or the general use of the regression. How can you tell if your model has been overfitted? Though, is it just from R square? Yeah, I should see along with R square. One thing I said, adjusted R square, right? Then there are other metrics which we'll see. So I'm saying blindly, just if you just go after R square, you will end up with this error. So you are not going blindly after R square. We will be chasing R square, but to some extent, we will then move over to adjusted R square. Okay, because it will further reduce my variables that are not significant. Okay, and we'll apply some other matrix. We'll see when we see the output of regression. Okay, clear? This point is clear, Angela, right? So in regression, overfitting can produce misleading R square values, regression coefficient, and p-value. Each model has its own quirks. if a regression model becomes tailor-made to fit the random quirks of the training data, it is unlikely to fit the random quirks of another sample or testing sample. Okay. Now, when new data comes in, when fresh data comes in, which or I want to test the model, it will fail because I have tried to overfit. I have not focused on the generalizability of the model. Okay. Overfitting a regression model reduces the generalizability outside the original data set. It occurs when the analysts start chasing high R square. Okay. Case of overfitting. Now, how can you this? You can just I've just given an example how in real life we try to chase overfitting. We just do overfitting. You can read through it later. Now, coming to how can you avoid overfitting? Yes, very important. Choose a regression model. How do choosing a regression model? When choosing a regression model, the goal is to approximate the true model for the whole population. In any prediction model, my goal is to approximate, not become God, not maximize, right? Not I would not try to maximize R square. Okay. If we accomplish this goal, our model should fit most random samples drawn from the population. Okay. That is why I am not saying my regression line will pass from each value. It will show the trend. That is why regression line is also called a trend line, right? It's 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 showing a trend, and of course it will have some errors on one side, some errors on the other side, right? Okay. This means our results are more generalizable. Our model will fit other samples. Our model is ready to be used or deployed on unknown data or a new data or a fresh data that comes up. Clear? Okay. To avoid overfitting, draw a random sample that is just large enough to handle all the terms or all of the terms you expect to include in the model. Investigate similar studies in the past before you collect data. Goal is to identify relevant variables and terms that you are likely to include in your final model. And after you get a sense of complexity of the model in your area, in your study area, you will be able to estimate a good sample. Okay, so these are some of the things you can take care when you try to avoid overfitting. Clear? Overfitting is clear. Now coming to multicollinearity. Now, as I said earlier, as we discussed earlier also when I was discussing correlation, that sometimes two independent variables come in and they are multicollinear. Means they have some correlation among themselves. That is called multicollinearity. Okay. So we'll see how does multicollinearity impact my regression model, right? Multicollinearity occurs when independent variables in regression model are correlated. This correlation is a problem because independent variables should be independent. Means independent variables should not have correlation. One, of course, you will see, you know, it creates redundancy. But here in regression model, what happens is, let's read further. It will further clarify how does correlated variable, how does it impact my regression line. The interpretation of regression coefficient is that it it represents the mean change in the dependent variable for one for each unit change in the independent variable when you hold all others the independent variable constant. Now, what does it mean? It means that the interpretation of the regression coefficient is that if I make a change in one variable, right, keeping all others constant, right? The regression coefficient that we are going to see, it assumes that all other variables are kept constant. So it shows only the change in that variable that my independent variable is making. Okay, clear? But what happens when multicollinearity is there? When independent variables are correlated, case of multicollinearity, right? The changes in one variables are associated with the shifts in another variable, right? So I have my y, and then I have y is explained by x1, x2, x3, right? Now x2 and x3 are correlated. So can this coefficient of regression, can it signifies a independent relation between y and x2? Leave x1? No, because a change in x will also make some change in y. Or sorry, change in x3 will also make a change in x2 because they are correlated, right? So it is difficult to understand the relation between x2 and y. Okay, so I'll repeat this. I'll read this again. When independent variables are correlated, the change in one variable are associated with the shifts in another variable. The stronger the correlation, the more difficult it is to change one variable without changing the other variable. Agrees? Right? Without changing one variable, I will not be able to change the other variable. Right? Thus, it becomes difficult model for the model to estimate the relationship between each independent variable and the dependent variable independently because independent variables tends to change in unison. Now x2, x3 are correlated, so when I increase, I want to see the impact of x2. I increase x2, x3 will also increase, right? The impact of x3 will also be seen on y. I cannot independently see the impact of only x2 because x2 and x3 are correlated. Are you getting this point? Multicollinearity, right? So when that happen, when this multicollinearity happen, it reduces the precision of the estimated coefficients and lead to unstable estimates. Now the coefficient of x2, because x2 and x3 are related, x3 is also impacting my x2. The coefficient of x2 is unstable, and because it is not, it is dependent on x3 also, right? And it leads to unstable estimates. It is unstable because there is a variation in x2 caused because of x3, right? So the variation in x in the regression coefficient of x2 is high because of multicollinearity with x3. Okay, which ultimately weakens the statistical power of the regression model. So when a variable, when an independent variable, there is a high variation in independent variable, it will ultimately impact my regression equation. It will ultimately impact the power of the regression model. Is this point clear? Multicollinearity? Type M if it is clear. Type M because too many Y's are there. So type M if this is clear. Okay, great. Thanks for the confirmation. So now VIF, variance inflation factor, is a variable, is a metric that measures this multicollinearity. VIF is the quotient of variance in the model with multiple terms by the variance of the model with only one term alone, right? It measures the how much is the variation that is coming when you have when you have multicollinearity. VIF identifies correlation between independent variables and the strength of that correlation also. It quantifies the severity of multicollinearity in an ordinary least square regression analysis, means in an linear regression, right? It provides an index that measures how much the variance of an estimated regression coefficient is increased because of collinearity. Okay, how much the variance of the estimated regression coefficient, right? That is increased because of collinearity. Now there are three, um, you can say three levels of VIF. VIF equal to 1 indicates no correlation between the independent. VIF between 1 and 5 suggests that a moderate correlation. VIF greater than 5 represent critical level of multicollinearity where the coefficients are poorly estimated and the p-values are questionable. Okay, so this is how we measure the multicollinearity. Clear? Okay. Is this clear to all of you, multicollinearity? Okay. Now, this is the output. We are going to, once we start working on R and we come up with the output, I'll come here and explain this, right? But yeah, then there is another important factor we should take into account or we should keep in mind is the interaction between the variables, right? Let's understand this and then we will take a break, and when we'll come back, we'll start working on the model, that is the wine, right? I have the data set, wine data set, and we'll start creating a regression model from it. Okay, so this is the output. I'll be explaining once we have uh, got the output from R. Okay, then okay, coming to interaction between the variables. Now sometimes what happens is in regression an interaction effect exists when the effect of an independent variable on dependent variable changes depending on the values of one or more other independent variables. Means in a regression equation an interaction effect is represented by the product of two. So not only, if you remember, our regression line was this, right? With a error term, of course, right? So I have x and x2, right? But sometimes what happens is my dependent variable is also getting impacted by x1, x2, the interaction of x1, x2, right? Right? So, and I have to keep that interaction also into the account. Otherwise, I will not be able to, my regression equation will not be robust, right? So when y hat is predicted, means y predicted is a dependent variable x1, sorry, it is talking about this equation where y hat is a predicted value of y dependent on x1, x2, which are independent variables here. It is just explaining this, and b0, b1 are the b0, b1, b2 are the regression coefficient, right? Here the same regression equation. Now here I do not have any interaction effect of x1 and x2, but if I have an interaction effect, my equation becomes this. Regression equation will be this. So this is the impact of interaction between. Now here b3 is the regression coefficient and x1, x2 is the interaction effect. Interaction between this and this x2 and x1 and x2 is called a two-way interaction because it is the interaction between two independent variables. There can be higher order interaction also, but we don't go into higher order interaction because it causes, I mean, it creates a lot of complication, right? Of course, for business, we don't go into that level of interaction, but yeah, if we have to, maybe you are uh, trying to predict some scientific data or some scientific project, then you might go into this because in science you need lot of precision. Okay, you might go into higher orders. Okay, to understand the potential impact a potential interaction effect. Let's compare the lines in the interaction plot. So these are two lines. We'll see this example. If the lines are parallel, there is no interaction, right? If the lines are not parallel, means they are intersecting somewhere, then it means there is some variable is anxiety, right? Plotted on y. This is the anxiety level. The independent variables is the dose plotted on x, right? So this is the dose. Researchers might hypothesize an interaction effect based on gender, right? They think that yes, there can be some interaction effect between gender. To visualize the potential interaction, they would plot the mean anxiety score by gender for each dose and connect the mean with the lines as shown below. So they plot the variable, uh, plot the x variable, which is the dose for each gender. In the plot, the lines are parallel. So if the lines are parallel, right, I bring in a variable gender, and if the lines are parallel, it means there is no interaction. If the lines intersect, it means there is some interaction. Okay, so that is all what we have to know in interaction, and that is what I have explained here also, right? So how do they interact when they are? That is what I have said. They x2, x1 and x2 are not independent, right? They are parallel. If they are, see, if they are this creates a parallel line, it means they are not independent. Sorry, they are independent. If there is some interaction, they intersect somewhere like this. Okay, so this is all right now on theory part. Now when we come back, I'm opening up the poll. I hopefully that gives you some sense and gives you a lot of insights on what is regression this session. And we have touched upon a lot of variables that impacts our regression line, right? So when we come back, we'll create a regression model and we'll see how do we choose the best regression model. For now, I'm opening up the poll. Please do participate in the poll and let us know how did you do in terms of patient delivery. The poll is open now and we will take a 17 minutes break today, right? We'll take a 17 minutes break. The poll is open now. Please do participate in the poll and I'll put up a timer. And please do come back as per the timer, right? Okay, thank you so much. And Okay, hello everyone. Thank you so much for participating in the poll, and uh, please give me a confirmation if I'm audible. Okay, so we will start. Yeah, I think I shared. Just check. Did I share it? If no, I'll share it. It's there, right? Okay, so uh, we have gone through a lot of conceptual part around R, around regression. Now let's start with importing the data set. So I'll show you the data set that you have import. Wine. Can you see this wine? So you have to import this wine data set. Line number 15 and 16 is good enough. Need not set the working directory. Line number 15 and 16. And let's take a look at the structure. Since I mentioned strings as factor equal to false, it did not convert any categorical into any categorical variable factors, right? So if I look at the structure, wine age, age is integer. Do you think this should be integer? Though it has integral values, right? We will convert this into numeric. Similarly, winter rain and harvest rain, right? I'll convert them into numeric because they might not take integral values always, right? So please convert these three variables into numeric. Sachin, wine is not found. It says wine not found. What should you make of this error now? I want, because I have solved this error. I have replied on this error multiple times for all of you. So I want some of you to take up and help. What is the issue? This is also a learning for all of you, right? Object wine not found. It is clearly saying object wine not found. Means it did not find object wine in the environment. Means you have written it, you have written this, but you have not run this. Line number 15 and 16. Run it and Explorer window will open. Then you will pick up the data set like this, the way I am doing. And then you will see wine in the global environment. Check the global environment. You should have wine data set, 25 observation across 7 variables. Now, some very interesting uh, analysis you can create using Psych package. Sachin, did you get it now? Okay. Psych package. Activate this package. I'm sure all of you would have downloaded it earlier, right? Psych package. Describe. When you activate the Psych package, describe gives you a very good insight on the variables. See, if I describe, it gives me variance, mean, standard deviation, trim mean, MAD, min, max. MAD is mean average deviation, right? Skewness, kurtosis, and standard error for all these variables. Okay, and in a very neat tabular format. I can view this also. See, okay. So describe and describe comes from Psych package. Okay. Pairs.panel. We have run this earlier. Pairs.panel. Did I explain this chart? Did I explain this chart earlier? Okay, let me explain this. A very powerful chart this pairs.panel creates. Have you have you run line number 40? If yes, then I'll proceed with this. Have you run line number 40? Others, just type 40. That will really help me. Okay, good. Right? So, now see this pairs.panel. What is it showing? It is showing the correlation between each variables, each of the all independent variables. It is showing the correlation which is written on the upper part, correlation coefficient. It's a command, Sachin. Then at the lower part, okay, in the diagonal, it is creating a chart, bar chart for each variable, right? And in the bottom part, it is plotting, it is creating a scatter plot of each individual variable. So this, can you tell me, this is a plot for which variable? Who will tell me? This is a plot for years coming here, years on x-axis and price on the y-axis. Okay, can you see this? Now, can you tell me this is a scatter for which two variables? Years on x-axis and AGST on the y-axis. Clear? So how AGST is moving with time? Okay, now who will tell me this one? Okay, let me ask you an interesting one. This one. Sorry, this one. Let's try and deduce some information out of it. Population and age, right? Got it, Nisha? Age and population, right? Did you notice both of them are independent and there is a very high correlation among them, right? So it means multicollinearity is going to be there, right? Also, notice that and notice and type of correlation. What is the type of correlation looking at the chart? High negative, very high negative correlation. And if you, I don't know why this is being printed very, the font is very small. If you see this, yeah, this one, 0.099. I hope it's readable at your end. Sachin, to understand these correlations, to understand the relationship between each variables, pairs.panel create this chart. So that is what we are doing. We are trying to analyze the variables before we start putting them in model. Okay. So high correlation 0.99. Okay, another thing. This one, year with age, and year with age is this one, and year with trans population is this one. Can you see? They both are inversely related with the years. One of them is having a positive correlation with years. The other one is having a negative correlation. Which one is having negative correlation with years? Age. And trans population is having a positive correlation. And that is why, of course, among them we have a negative correlation, right? So that is what this chart can really help you getting a glimpse. In a single chart I can easily see which one of them is having what type of correlation. I don't know why today these are not readable, but at your end are these readable correlation coefficients? Yes, some issue at my end, maybe some screen issue, right? So you can, if you go through these, you will easily figure out where there is a high correlation, where there is a less correlation, right? Okay, so pairs.panel, very powerful chart. It creates a very powerful. Okay, now these are just some plots. We are not going to do it. I'm just showing you the individual plots with price, right? I've already shown this in the discussion earlier, right? So you can create them later, right? Okay, correlation and covariance. Now, as we can see, we have figured it out. Let's calculate the correlation between age and France population, right? So you'll see it's coming out to be 0.99. Correlation Wine, if I run this, it will create that matrix, correlation matrix. Okay. So if I put this in view, it will be better. Yeah. Okay. Correlation, the same thing. It's the same thing, right? But yes, in a different way. Okay. Covariance. So it is calculating the variance, though it's not required. Correlation is what we need. Now, let's run the model. Let's create a regression model. And regression model is created with the command LM, line number 82. LM means linear model. Okay. Right now, I am going to create a regression model with only price as dependent and AGST as independent, just the way we moved in our explanations, in our discussion also, right? So the command used to used to create a linear regression is LM. Within LM, I mention price on the right side of tilde, sorry, left side of tilde, and AGST on the right side. Just the way you write equation y is equal to x. And I mention data, and I create a model 1. First model I have created, right? Notice R square multiple R 0.435. Remember, the same was there in the explanation also. It was 0.44 single variable, and adjusted R square is 0.41. Okay, so we are going to concentrate more on adjusted R square. Okay, I am going to explain this output in a bit as we generate a output from multiple variables. For now, this is the output that R has created when we run a regression model. How to get this output? Run summary model 1, line number 84. Once you're done, let me know. Once you're done with summary, type 84. Could you please explain line number 82? Sure. Okay. Angela, in 82, I am creating a linear model. Means I am creating a regression model, right? So LM price variable. Wait, I think I did not attach. Okay, I mentioned data price. That is LM means linear model, Bharat. Linear model means regression model. So regression, linear regression, we created using LM command. Okay, Angela, price, which is my x variable, tilde. Right now I am only using one variable AGST, and I mentioned data equal to wine. Is that clear, Angela? Any query in it? Any further doubt? Let me know. I assign this to model 1 so that when I run a summary, or I can do this way also, summary, and instead of model 1 I put this entire thing, but it's better to assign it later on for reference, right? So I assign it to model 1, and I get some output also. I hope you've seen, all of you have seen some output there, right? Some numbers written, some complicated output. We are going to see that. When I explain this output, we'll come to that. Okay. After this, calculate the residuals and sum of squared of errors. Residual means and sum of square of errors. So you calculate the residuals with the command in the model. Notice, okay, notice that when you do a summary of model, right, you have components, residuals, coefficients, residual standard error, multiple R square, adjusted R square, p value, and F statistic. So these are the variables that my output has produced. Okay, right? Of this, what I am doing is I am squaring the residuals, which is the errors. Residuals give me the errors. I am squaring all the residuals. This is giving me only the minimum quartile median of the residuals. But what I'm doing is I'm squaring all the residuals and doing a sum of it. That will give me SSE. So if I have a single variable, remember my single variable, the explanation that I've done on SSE value was 5.73 only, because and multiple R square, that is the R square, I could bring the best R square that I could bring using a single variable was 0.44. Yes, let me quickly show it to you. 0.44 and 5.73 with a single variable. That is the best SSE I can get, right? Just recalling, right? Got it, all of you? Now let's add more variables. Let's add one more variable. I add harvest rain. So name this model as model 2. Now keep the naming consistent so that whenever we have the output, uh, we have a consistent output. So line number 97 to 101. Same thing what I have done till now. Just that I have included two variables. AGST plus harvest rain. When you're done till 101, type 101. So what is the SSE? Sorry, what is the SSE? Sum of squared error has further reduced. Did you see? When I am trying to predict my price with two variables, AGST and harvest rain, I am further able to reduce my sum of square of errors. Everyone got the same 2.97? All of you got the same thing? I'll wait for some confirmations. If you have done till 101, type 101 in the chat window. Okay, now one more thing is, and a very important thing is, that creating or arriving at a best model is a iterative process. Iterative process means you have to try different iterations, you have to bring in different inputs, you have to bring in even the advice of a industry expert. Alone data scientists cannot come up with a model that is robust enough to suit or to fit the new data or to fit the data that is live data, that is live, right? You will have to involve industry experts. We are going to see that in this example where the industry expertise is needed. Okay. Okay, so now we have seen two variables. Now next I am going to add all variables. Now why? I'm just trying putting in more variables and trying iterations, right? Just put all variables. Okay, when you put two variables and you look at the output, it looks something like this, right? There are some star ratings, right? All this we are going to learn when we create a model with all variables, right? So coming to model with all variables, line number 106 and 107. Now, to use all variables on the right side, we use a dot. Can you see dot? I will I will use a dot. Dot on the right side means pick up all the variables. You need not name them, right? So when you run line number 106 and 107, you get this output. Please run line number 106 and 107. So you got all of you getting the same output. Here, if you observe closely, my age is giving me NA. Can you see NA against age? Why is it not? Yeah. All of you are getting NA. Now, why is this NA coming? See, when I put all variables with a dot, right? Age becomes NA. It is because error not defined because of singularities means there is a strong correlation between age and population. We have seen that, right? So, what is linear model doing? It is just picking one variable, France population, and leaving the other, right? Because it has seen at the back end, it has seen that one variable is good enough, right? So it is leaving age, right? But tell me, now here comes the industry expertise. Do you think we should be leaving age? Age of wine is a very important variable to determine the quality of wine, and industry expertise will tell you this. Not as a data scientist, you will know because some of you might not be that closely observing this industry, right? But when you discuss this output with some industry expertise, they'll say age cannot be a insignificant variable. Age, you have to include age, right? But why this age is coming as NA? Here, the reason of age coming as NA is because there is a high correlation between age and population. So it has taken population, right? Model has taken population because the impact it has seen whether it puts in age or population, the impact is going to be same, right? But if I want both age and population to be shown or to be used in the model, instead of dot, see in dot, I am not explicitly specifying the variables to be used. I am just saying use all variables. So instead of dot, I add age explicitly and I create model 3.1 wherein I am naming all the variables. Okay, I'm naming all the variables, age and France population both. Now when I run this model 3.1, line number 116 and 117, sorry, please run line number 116 and 117. NA is gone because I have explicitly mentioned age. Okay, now this is the output. We will. Why dot does not work? Since doesn't work, sir. Yeah, Bharat, dot did not work. See, because dot did work actually. Dot did work, but what it did was because there was high collinearity, multicollinearity was there between age and France population. The impact is going to be same because both these are correlated. They're going to have a same impact on the y variable, right? Yes, because they are highly correlated. The impact is going to be a similar one, right, on y variable. So what it has done is age is giving error not defined because of singularities means what does this mean? Error not defined by singularities. See, here it is written. One not defined because of singularity. Singularity means it is picking only singular data, not correlated variables. Singular variables means independent variables, right? Okay. So these two, age and France population, are correlated. So unless and until you ask it specifically, here I am asking R to specifically linear model to specifically include both of them. There I just use a dot, right? So it's kind of a, it has given me this message, one not defined because of singularities, means because of correlation between them, it has not included one of the variable. Okay, but I want just to see, I want to see the impact if I include both age and France population. How is my R square, right? So I include both of them in my model. Okay, and I come up with model 3.1. Now here, if you see model 3.1, this is the output that you should be getting. All of you are getting a similar output. Don't go into the detail. All you just do is check R square. Check this R square value. What is the value of R square coming up for all of you? Should be close, 0.82 only, right? Yes, 0.8294, right? Right? So we have come up with the R square value, and let's take a look at the adjusted R square. We know what adjusted R square is at least, right? But now what we'll do is we'll understand all these remaining, we'll understand this entire output of regression. Looks like scary at first. Those who are seeing this output first time, it looks lot of scary numbers, right? But we'll try to decipher it. We'll try to understand each and every element here, right? Okay, first thing, let me start with residuals. Residuals, you know, these are the errors, right? It is giving you the minimum error, maximum error of the. Okay, who will tell me how many uh, data points we had? If you had seen structure, you can run structure and tell me how many data points we had. 25, yes. How can we save the output in the console when we open? You cannot save the output in console. Remember, Angela, I told you in the first session, when you save this file, only this part gets saved. This, of course, some variables that you create, they are saved in the global environment, but you can't save this chart and the output in the console. Okay. So whenever you open R, you'll have to run to get these output. Okay. Angela, I hope that answers your query. You will definitely, you will be able to save this, and you have seen I'm sharing you these files, the R script files. Okay. But not console. Okay. Okay. So we were, yeah, I was discussing. And what if we want to copy the charts? You mean these charts? Charts here, right? That you can download. See, export. You can export these. Okay. You can export. I can export this. See. Okay. Okay. Can we proceed? And but definitely not the console thing, because it's a short-term memory. It is running the recent commands. You keep on clearing it also, and it's a good habit also to keep clearing the short-term memory. Otherwise, over a period of time, if you are running too many commands, R will get slow. I mean, the performance is going to be impacted. So you should keep clearing the uh, these commands. Okay, this console. What is this coming up? Just give me a minute. Okay. Anyways, there's some, I don't know why this transparent window has come up and I'm not able to click there. Anyways, I'll manage it without. Okay. So, yeah, I was explaining the output. So yeah, I asked the question, how many variables, how many observations we use? 25 observations, right? Right? So of the 25 observations, if I calculate the residuals, right? The price that has come up from this model with the actual price, these are the residuals that will come. Okay, minimum will be this and maximum will be this and median is this. Okay, now let's understand this from coefficient till last line. We are going to go back into the presentation or the where I have explained these in detail. So this is our output, right? This is our output. Let's understand this output. You have the first row in the output is the intercept. Intercept, remember, y is equal to mx plus c. C, this is the c part. Okay, constant part, b0, right? Okay, next. So my regression line is going to be, let me write the regression line from this, right? You will get an idea. My regression line will be price equal to, let me write x1. X1 is my AGST. So AGST, sorry, it will be coefficient. These are the coefficients. Okay, these are the estimate. A is the coefficient. This, with this column A estimate, you can create the regression line. My regression line is, as I said, it will be, let me write it in a neat way so that you can, what I'll do is I'll write it here in notepad just to make you understand. So my regression line is going to be price equal to 0.06012 AGST. Now 0.0612 is coming from here. Notice it's e to the power minus 1. So I moved, I think it's not 0.6, it should be 0.6. Okay. So this is e to the power minus 1. You know exponential? You know how to read this, right? Plus. It will be minus for harvest rate. So I'll put a minus 0.003958 multiplied by harvest rain. Clear? Plus age 0.0005847 into age plus 0.001 whatever it is, 043 winter rain. And last, minus 0.00004,953 into trans population. Did you get it? How do you write the, how do you know the regression equation? Though you don't have to write it, but what I am telling you is these at A are the coefficients of regression equation. Is this clear? If you want, I can share it also, but not required. You don't have to write the regression equation. Okay, so this first part is, oh sorry, I missed one part, very important part, which is the coefficient. This is fine. I missed the coefficient. Yes, Sachin, right. Minus 0.4504, right? That is the coefficient. This is the first part, constant, right? That's not a coefficient, sorry, this is a constant, right? B0. Okay. We share this equation. Yeah, I can share, but you don't need to write. You just have to be knowing, right? You never have to write it, but yeah, you can take it, not an issue, right? Okay. So this A part gives you constant, which is the intercept, and the coefficient of the variables. Clear? First part is clear? Okay. So let's see. Now I go to this. This is the explanation. Estimate A gives the coefficient estimates of the intercept of the independent variables of the model, right? Now, B plus C plus D helps in estimating. Now, what are the B plus C plus D? B, C, D. You can just ignore this slide. It is the same output, but I think it's clearly readable here, right? So, it's the same output, right? Okay, so B plus C plus D helps in estimating if the variable should be included in the final model or if the coefficient is significantly different from 0. Now, what does this line says? Helps in estimating if the variable should be included in the model. So, only the statistically significant variables will be included. If a variable is statistically significant, only then it will be included in the model. All of you agree? Please, I want response. I know it might be a little bit overwhelming, but this is a very important part. After this, you can be relaxed, right? So, only, I repeat, only the statistically significant variables will be included, right? So, looking at this equation, can you tell when will a variable be not statistically significant? When will a variable be not statistically significant? When I make this coefficient 0. Yes? Agreed? When I make this coefficient 0, it will become statistically insignificant. Means then that variable do not has a correlation with price. Agreed? That is what it is mentioned here. Or if the coefficient is significantly different from 0, means if the coefficient, what we are going, this B plus C plus D is going to help me understand if the coefficient that I am writing that is significantly different from 0 or it is 0. Okay? It helps in estimating the variable should be included in the final model, means, or if the coefficient is significantly different from 0. A coefficient of 0 means that the variable is independent and does not impact my dependent variable. That is what is the crux, right? Hence, it is not statistically significant, important, and hence not included in the model. Do you get this explanation? Right? Now, let's see. Let's go further. B is the standard error. right? Standard error is nothing, as the term also says, it's the standard deviation of the estimate. Means if you calculate this over the period of time, what will be the standard error that can come? What will be the standard deviation of each estimate? So what it is saying, the standard deviation of this AGST is this. Standard deviation of the coefficient of AGST, sorry, right? Standard deviation of this value is this. Standard deviation of this value is this, right? So standard deviation is always a positive number. Remember, standard deviation is never a negative number, right? It is the variation. It is showing the variation only, right? So it is the standard deviation of the estimate. That is the variability in the coefficient value. If we repeat the sampling, right? If we keep repeating the sampling and run the model, this is the maximum variability. This is the variability of the value. So it means lower the standard error, the model will be able to estimate the coefficient with greater precision, right? So this gives a measure of how much the coefficient is likely to vary from the estimated value of the coefficient. Standard error of the coefficient is always positive, right? So it means what we should be looking at is that this value should be low, as low as possible. Lower the value, more is the possibility that it is a significant variable, right? Variability is less means, right? But here the story does not end here. It goes further. It calculates the t statistic, t value. T value is the estimate upon standard error. So means A upon B is the t statistic. Larger the absolute value of t statistic, more likely the coefficient of the variable is likely to be significant. When will t value be more? When the standard error will be less, right? Yes. Lower the standard error, more will be the t value. Simple division, right? So that is what it is saying. Larger the t value of the absolute statistic, larger the absolute value of t statistic, absolute value, more likely the coefficient is likely to be significant in the determining the value of dependent variable. The smaller the standard error, higher the chances of the variable being significant. So that is what I said earlier. Smaller the error. Now notice absolute values, t value. Let's look at the absolute t values. Which are bigger? These two are bigger, right? Absolute, right? Hence is this star rating. This star rating with 3 star, I'll come to that also. It gives you how significant the variable is. Notice significance code. If there is a 3-star rating, it means there is a high significance. These are highly significant variables. If star rating are 2, it means the significant, it means it is lesser significant than 3, and then so on. Then 1 star, then dot, then nothing. Okay. So right now we have 3-star ratings against these two, and no wonder we are having the maximum t values here. Okay. We have to look at the t values having absolute t values. More the absolute t values means more is likely, more the variable is going to be significant. High that variable is going to be significant. Okay. Fine. Small. Yeah. P value. Now the last column, p value. It measures how possible. Now what this p value measures, very important, because p value is anyways important. It measures how possible it is that the coefficient is actually 0. What is the probability that the coefficient is expected to be 0? Because only then if the coefficient is 0, then the variable is not significant. I've written here also, I just should discuss that, right? So that is what p values give you. So it means smaller the p value, lesser is the likelihood that coefficient is going to be 0. P value is the probability of the coefficient becoming 0. So smaller the p-value means more significant the variable will be. Yes, everyone agrees to this. So if it is more significant, then the row is statistically included. Yes, yes, yes. If it is more significant, then I'll include that variable, right? Okay, Bharat? Okay. So you got it. What you have to look, if you have this output, you have to look at p-values. Just double, to be double sure, you look at the t values also, absolute, that they are bigger. Yes. T values should be the smallest, and you look at the star ratings, which is saying these are the most significant of the variables. Okay. Quickly, now we'll wrap it up. Smaller, I've already discussed. This number will be large when absolute t value is small, and small when absolute t value is large. You can see the correlation. This number, can you see absolute t value here? Absolute t value. So this number is coming out to be very large. P value is very large. It means when I put in all variables, model is showing age is not significant. What is happening is when I put age and France population together, model does not include age and France population. So it means I have to either include age or France population, and the industry experts will tell you to include age of the wine, which is definitely more significant, right? Because industry expertise come here, right? Okay. So this output is clear. Now you can make sense of this output. Now there are some more terms below of this. You know what is standard R square, or you know what is adjusted R square, right? So we'll quickly see the remaining ones. I've already explained these two. Yes, Bharat, but we still have to decide on the final model. Just hold on, right? I've just explained the output using all the variables. I put all the variables, but this is not the final output. We still have to work on it. Okay. We have a term called residual standard error, right? What is this? On 19 degrees of freedom. So residual standard error, also called the standard error of the model, standard deviation of the errors. Root mean squared error, basically. In general, it quantifies how well or poorly the model is predicting the values of y variable on an average. It can take, it can also be taken as an average error of the model. This is the average error of the model, right? Right? This is the average, and notice how many variables that I am including in the model. 25 minus 1, 2, 3, 4, 5, 6 is your degrees of freedom, 19. So this, you just have to be sensitive about it, 19, right? 25 is the total, minus this 6 will give you the degrees of freedom. Bharat, just hold on. Let me complete this, right? This is the last part, and then after that I'll take up your query. We still have to run the final model, right? So just hold on. Your query will be, okay, I'll repeat B part. Just hold, right? This last thing, F statistic, measures the significance of the overall model and not just one variable. Now, this measures how significant the overall model is. Now, this is used, F statistic. Where is F statistic? Here is it. If I have to compare two models, right? Then I also use F statistic. Bigger the F statistic, better the model. Better is the model. Okay, you just have to remember this. When you are looking at the output and you are comparing two models, bigger F statistic means better is the model. Okay, clear? So that's how the output, how you interpret the output. Now, yes, Bharat, what do you want me to do? Estimate B. What is estimate B? Okay, this one. It is the standard deviation of the estimate. See, this is my estimate coefficient of regression equation. I created a regression equation from this, right? Now, if I keep running this model, keep running output again and again using different um, data, right? You getting more data and keep running that, keep coming up with model, right? New models, right? What will be the standard deviation of this, right? It standard error tells you the standard deviation of the estimate. It is the variability in the coefficient value if we keep repeating the samples. I take another sample on the same, right, data. I take another sample from the population and run the model. I will, of course, I will not get the same coefficient. I'll get some different coefficient, right? So there will be some standard deviation of the estimate. This is giving you that. Okay. Okay. Now, I think all of you have run this 3.1, right? Okay. I I will show this in R Commander maybe later, but you can try this in R Commander. I'll show this in R Commander in the last session, right? The same thing. Right now, let's complete it. Okay. So now, since I have included all the models, all the variables, and I have seen my R square is 82.94, means 0.8294. Adjusted R square is 7845. But as I said, I can see age and France population. I cannot include both of them, right? So I will run model. First, I will remove France population and create another model, model 4. So I'm sharing this model. I'm sharing these codes. Run this model 4. If you look at R square now and adjusted R square, note that now age has, when you run this, when you run model 4, which I have just shared with all of you so that you don't have to write it, can you take a look at the significance of the variables? Has age become a significant variable? Sachin, just hold on. I'll check for that R Commander, right? Just hold on, right? Age has become a significant variable, and the industry experts will tell you that yes, age has to be included. It's a significant variable always for determining the quality of the wine, right? Age has now become a significant variable when we remove France population. Earlier it was not. This happened due to multicollinearity. I have seen that because there is high degree of correlation, right? Okay. This is again, I'm just calculating the correlation which I have already calculated, so you know it. Correlation. Okay, this core plot. Install this package core plot. It will create a plot. This is also very interesting. It will create a plot showing the correlation. See, it will create this plot. The color represents the positive and negative correlations. Okay, so high correlation between age, high negative correlation between age and France population, negative correlation. Okay, core plot. Note that the age of wine and France population are inversely correlated. The France population has been on the rise from 1952 to 678. Thus, if the wine belonged to older years, means France population was lesser, right? higher correlation between predictor and dependent variable is good thing for the model, but multicollinearity is not a good thing, right? Variables are highly correlated, can create problems. This is all about multicollinearity that I have discussed. Hence, we should look for a way to remove them, insignificant variables one at a time. So, remove the insignificant variables one at a time so as to arrive at the best model. So, you do some iterations like the iterations we are doing. We removed France population. I will remove I will remove age and check, right? I have now in this model 5, I have removed age also, right? Uh, Along with France population, I have removed age also, and I see that R square and adjusted R square reduce. Can you see R square and adjusted R square? They have reduced, right? So it is clearly indicating that if I remove both of them, I am losing out on some value, right? Because my R square and adjusted R square are reduced. But we know age is a significant variable and more intuitive, and industry expertise also vouch that. So we will choose model 4 which has age in it model 4 instead of model 4 which has France population in it. I will choose model 4.1 which has age in it, right? So I'll run one model 4.1 again, and we'll look at the adjusted R square. And notice it has the maximum F statistic also, right? If I compare it with other models, F statistic, it has a better F statistic also. All these are indicators that we are going to go with a model which has age in it. Okay. Even though if I exclude age and include France population, right? And I look at the output R square and adjusted R square. It is slightly better when it is there when I include France population. Very minutely better. 82.94, there it is 82.86. Right? 79.43, and here it is 79.52. Slightly better, but still with the inputs from experts, industry experts, I will still choose that model which has age in it rather than France population. Is that clear? Right? So all of you will choose 4.1 model. Now we are going to, now this is the training data on which we had created the model, right? I have another data set, wine test 8 years. Quickly, I want all of you to import this data set. Name it as wine test, line number 200 and 201. I want all of you to run line number 200 and 201 and pick up this data, wine test 8 years. I am also doing it. Studio training regression. Now I will try to predict this with a command predict model 4.1 and new data equal to wine test. Here notice in predict we mention new data as the command. It's not data, it is new data. Line number 205 and 206. I'm sharing it so that you can quickly write it. And if I predict this, I get some values. Let me also get the values, actual values. Run 205, 206, and then run 212, line 212. So predict test will give you the predicted values of the model, and wine test dollar price, line 212, will give you the actual values. Okay. So this is your testing data, right? So can you look at how closely my model could predict? Yes. Look at the first value. Actually, it was 6.77. Sorry, actually it was 6.95. My model predicted 6.77. Second value, 6.49. My model predicted 6.68. Third value, there was a difference in the third value. It did not predict very accurately the way it predicted 1 and 2. Look at the fourth value, 5.98. Model predicted 5.97. Getting it? All of you got this? Now, comparing, I can also calculate the SSE for this. And if I look at the SSE or R square of this, 1 minus SSE upon SST, line number 22, 222, 223 and 224. You'll see my R square, 8233. Okay. How many of you calculated R square with the predicted? So that is the variation my model is explaining even on the test data, right? Which is very close to that the R square in the training data, right? So it means my model is doing pretty well, fairly well, even on the testing data. Bang on time. Exactly 9, and we have been able to do this. Otherwise, I was thinking we might have to extend this session. Okay, so that's it on regression. Hopefully, this session added value. You learned a lot of things on regression, right? How to read the output, how to select the model, and a lot of things. What is multicollinearity? What is overfitting? And hopefully, it was a useful session for all of you, right? So we'll continue. We will continue our journey. So we still have a long way to go, wherein we have to do logistic, we have to do SVM, then a lot of other models are there, right? Okay, Sachin, right? So all of those, if you want to leave, you can leave. Let me just, Sachin, can you show? Sachin, it's clearly mentioned Shapiro test is there to test the Shapiro test is there for testing the normality, right? Yeah, Angela, please say again. In predicted test output is one the accurate or actual or predicted. Sorry. In predicted test output. Sorry, Angela, I could not get what you're saying. Please say again in predicted test. Okay. Okay, test 1. Output is 1, the actual or predicted. These are predicted. This predicted test is giving me the predicted output in the console. Okay. Okay, this predicted test 1. This is my predicted test 1. Right? These are my predictions made by the model. These are my actuals. I have picked it from the data. That 8 observations. If I open this, these are the 8 observations. Okay, I hope that is what you're saying. These are the predictions from 1, wherein I have included age. These are the predictions from 2, wherein I have included France population. Okay. Yeah. I have calculated the SS. I have calculated the R square using both 4.1 and 4.2. Okay. Yeah. But we have to see getting inputs from a expert. We will go with the age, right? But because age and France population was so highly correlated, even France population is giving me a good based on this data. But it could be that France population growth normalizes in future, but still age of the vine is going to remain a very important factor, right? In the data that I have collected, France population and age was having a high correlation, but in future it might be France population starts not growing or starts normalizing or start reducing, but still age will remain a important factor. Okay, these are the inputs of the industry expert. Okay, so that's it. On that note, we'll continue next week. Please do keep practicing and keep learning, and we'll continue our journey next week. Thank you. Take care.